Hello, my name's Clinton, and I'll be your guide through this final module of Day 8. We're going to talk about inverse trig functions. Please don't forget to pause this presentation at any time if you need a bit more time to think about something. We've been speaking about inverse functions, and in this module we're going to look at the inverses of some other functions you're familiar with. Remember the trigonometric functions, which comprise the functions sine and cos, as well as other functions derived from them, like tan, sec, and cosec. The sine function is the first we're going to discuss the inverse of. The full sine function, which extends infinitely in both directions, cannot have an inverse, as it fails the horizontal line test, which we saw last time. This fits in with our understanding of the sine function, since solutions to equations like sine x equals 0.5 are infinite in number, because the sine function is periodic. So we are unable to say which specific value has a sine of a half, since many values do. We dodge this issue by restricting the sine function to a smaller domain, namely the interval between minus pi on 2 and pi on 2. On this smaller region, the function does now satisfy the horizontal line test, so will have an inverse. Again, if we know that sine x is 0.5 and also specify that x must be between minus pi on 2 and pi on 2, then there is now a single unique number x with both of these properties. We can now proceed to discuss the inverse of the sine function on this interval. The domain of our restricted function is minus pi on 2 to pi on 2, and its range, that is, the possible output values, is minus 1 to 1. This means that the inverse function will have domain minus 1 to 1 and range minus pi on 2 to pi on 2. Here's the notation we'll use. For x between minus 1 and 1, y equals sine to the minus 1x means that x equals sine y, and that minus pi on 2 is less than or equal to y is less than or equal to pi on 2. It's important to remember that sine to the minus 1x has nothing to do with the reciprocal of sine x, that is, the fraction 1 on sine x. It's just convenient notation for the inverse function. Here's the graph of the inverse sine function. It's just the graph for sine in our restricted interval, reflected in the line y equals x. How about the inverse of the cosine function? If we look at the graph of y equals cos x, and restrict to the interval from 0 to pi, then the function now passes the horizontal line test, and we can define an inverse. Here's what the graph y equals cos to the minus 1x looks like. It has domain from minus 1 to 1, and range from 0 to pi. Finally, let's look at the tan graph. Remember, y equals tan x repeats every pi, and has vertical asymptotes at every odd integer multiple of pi on 2. If we restrict now to the interval from minus pi on 2 to pi on 2, remembering that the round brackets mean the interval is not including its endpoints, then the tan function does satisfy the horizontal line test, and so we can define its inverse. Try to think about what the range and domain of its inverse will be, and have a go at sketching the inverse curve. Press pause and try these exercises, and press play when you're ready to continue. The domain, minus pi on 2 to pi on 2, of our restricted function becomes the range of our inverse. The restricted tan function has range the whole of R. If you don't believe this, go back and look at the graph again. This means that R will be the domain of the inverse function. The graph looks like this. Again, notice it's just the original tan curve reflected in the line y equals x. Now let's see how to apply our calculus methods to these functions by computing their derivatives, starting with the inverse sine function. Remember that y equals sine to the minus 1x means x is sine y. Then differentiating with respect to y gives dx dy is cos y, and inverting this equation on both sides, we see dy dx, which is what we are trying to compute, is 1 over cos y. We need to get rid of the y on the right-hand side. But cos y is the square root of 1 minus sine squared y, taking the positive square root because we're considering y between minus pi on 2 and pi on 2, so cos y must be positive. And sine y is x, so this means cos y is the square root of 1 minus x squared. This means dy dx is 1 over the square root of 1 minus x squared, where y equals inverse sine x. More generally, if our function is y equals inverse sine of x on a, then we can use the chain rule to see its derivative is 1 over the square root of 1 minus x on a all squared, by the previous slide, times 1 on a, as this is the derivative of x on a. Putting this into a single fraction, and then putting everything under the square root sign over a common denominator, and then cancelling the square root of a squared, which is a, on the bottom of the square root with the a out the front, we see dy dx is 1 over the square root of a squared minus x squared. Have a go at trying to find the derivative of the inverse cos function. Press pause, and then press play when you're ready to continue. Remember, if y equals inverse cos x, this means x is cos y. So dx dy is minus sine y, which means dy dx is minus 1 on sine y. Using our trig identity again, sine y is the square root of 1 minus cos squared y, which is the square root of 1 minus x squared. Again taking the positive square root, so dy dx is minus 1 over the square root of 1 minus x squared. Finally, let's see how to differentiate the inverse tan function. We'll need to remember another trig identity here. Remembering that y equals inverse tan x means x equals tan y, we have dx dy is d dy of tan y is sec squared y, because the derivative of tan is sec squared, so dy dx is 1 on sec squared y. Here's where the trig identity comes into it. We know 1 plus tan squared is sec squared, so sec squared y is 1 plus tan squared y, which is 1 plus x squared, since tan y is x. So dy dx is 1 over 1 plus x squared. Have a go at these practice questions, which will give you some familiarity with derivatives of inverse trig functions. Press pause, and then press play when you're ready to continue. Here are the answers.